Imagine a future where computers can crack problems in seconds that would take today's most powerful supercomputers billions of years. A world where information moves instantly, not through wires or signals, but through the laws of physics themselves. That future just got a major boost. Today, we're diving into a revolutionary breakthrough from the University of Oxford. Scientists there have successfully teleported logical quantum gates between two separate quantum processors. Yes, teleported. And no, this isn't science fiction. Let's break it all down. First off, what is quantum teleportation? Unlike what you've seen in movies, we're not transporting physical objects from one place to another. In quantum mechanics, teleportation refers to the transfer of quantum information, not matter. This is made possible through a phenomenon called quantum entanglement. When two quantum particles become entangled, they form a pair so deeply linked that the state of one instantly determines the state of the other, regardless of the distance between them. If you change the state of one particle, the other reacts instantly, as if they were still physically connected. Einstein famously called this spooky action at a distance. Through this process, scientists can transmit the quantum state of a particle from one location to another without moving the particle itself. This is where Oxford's work becomes groundbreaking. Previously, quantum teleportation was used to transfer individual quantum states, already a big deal. But now, Oxford researchers have gone further by teleporting logical quantum gates, the actual operations that process quantum information, between two separate quantum processors. To understand why that matters, let's step back. In classical computing, logic gates are what allow your computer to make decisions. Things like and, or, and not gates, working with zeros and ones. In quantum computing, these gates work with qubits, quantum bits that can exist in multiple states at once, thanks to a property called superposition. So when Oxford teleports logical gates between distant processors, they're essentially connecting two quantum computers to act as one, without any physical connection. This is like creating a digital nervous system made of thin air. Why is this such a big deal? Because it solves one of the biggest limitations in quantum computing today: scalability. Most quantum computers today operate on a single chip with a relatively small number of qubits. But the more qubits you add to that chip, the more unstable the system becomes. The information gets noisy, and error rates go up fast. The Oxford method sidesteps this problem. Instead of building one massive, complicated quantum chip, we can now build smaller, modular quantum processors and link them together using teleportation. Think of it like a network of small brains working together as one superbrain, without being physically wired. This modular approach opens the door to creating much larger and more powerful quantum systems, the kind capable of running complex algorithms that would take traditional computers ages to complete. And here's what's really exciting. This isn't theoretical. The Oxford experiment was done with current technology. It worked. That means scalable quantum computing just became a lot more realistic. There's another major implication: the idea of a quantum internet. Today's internet relies on classical communication and encryption. Data is secured by mathematical problems that are hard to crack, but not impossible. Quantum computers will eventually break today's encryption methods. That's a ticking time bomb for cybersecurity. But a quantum internet built on teleportation and entanglement would be fundamentally unhackable. Here's why. In quantum mechanics, measuring information changes it. If someone tries to intercept quantum data, it disturbs the system and reveals the intrusion. It's not just secure, it's self-protecting. That could revolutionize everything from government communication to financial transactions, creating a world where digital eavesdropping becomes a thing of the past. Now, as exciting as this is, we're not ready to build a full-scale quantum internet or global teleportation networks just yet. There are still major challenges to overcome. One of the biggest is quantum coherence. Qubits are incredibly fragile. The slightest interference, heat, vibration, electromagnetic fields, can knock them out of their delicate quantum state. We also need advanced error correction. Unlike classical computers, we can't simply copy quantum data to make backups. Any attempt to duplicate or observe a qubit's state changes it. That makes quantum systems extremely difficult to debug. Another challenge is scaling. The Oxford team teleported gates between a small number of processors. To build a truly global quantum system, we'll need to reliably perform teleportation across much longer distances and in more complex architectures. In other words, this is a first step, but it's a huge one. So what does all this mean? Oxford's breakthrough in teleporting logical quantum gates isn't just another cool experiment. It's a foundational moment in the evolution of quantum computing. We're now one step closer to creating modular, scalable, secure quantum systems, the kind that could change the way we solve problems, communicate, and protect data. It's also a sign that quantum mechanics, long viewed as an abstract theoretical science, is becoming engineering reality. The future of computing won't just be faster, it will be fundamentally different. Thanks for watching. If you enjoyed this breakdown and want more insights into the next era of technology, make sure to like, share, and subscribe. This is just the beginning. I'll see you in the next one.